Hello, welcome to physical chemistry tutorial number 1. Today we're going to talk about normalizing wave functions. So we are asked to normalize the following wave function, psi equals sine of pi x over 2, where all space is defined from 0 to 1. So the first step with any normalization problem is to recognize that we need to take the integral over all space of the complex conjugate of psi times psi d tau and set that integral equal to 1. So what is the complex conjugate of psi? Well, the complex conjugate of psi is essentially psi, but you replace I, where I is the complex number, with negative I, and you do this for all I. So here, we don't have any i's in psi, so we're going to say that the complex conjugate of psi is basically psi, because we don't have any i's to replace with negative I. And then finally, we need to introduce a normalization constant. So we're going to rewrite psi as n psi, where n is the normalization constant. And we should also write the complex conjugate of psi as n psi complex conjugate. And now we're ready to complete this problem. Alright, let's solve this problem. So recall that we're going to take the integral over all space of psi complex conjugate multiplied by n, and we're going to multiply that quantity by n times psi d tau, and we're going to set that equal to 1. So in this case, d tau is simply dx because we're in one dimension. And remember, all space was defined as the interval from 0 to 1, including 0 and 1. So now let's make some substitutions. So we're integrating from 0 to 1 of n psi. Remember, in this case, psi complex conjugate and psi are the same thing because there was no i's, times n psi dx, and we're setting that equal to 1. So now we have n times sine of pi x over 2 times n sine of pi x over 2 dx. We're setting that equal to 1. Now recall that n is a normalization constant. Constants can flow out the integrals, so I'm going to take both of these n's out, and I'm going to multiply these sine terms together. And so when I do that, I'll get n squared. Remember, I have n times n. They float out the integral from 0 to 1, and then I also have sine squared of pi x over 2 dx, and that's set equal to 1. Okay, and so now we're ready to solve this integral. There are two ways to solve this integral. I'll be showing both ways. Okay, so now let's evaluate the integral using the direct method, using math without using a table. So recall that we have the integral from 0 to 1 multiplied by n squared sine squared of pi x divided by 2 dx, and that was set equal to 1. So I'm actually going to use a trig identity here. So sine squared of x is equal to 1 minus cosine of 2x all over 2, which is equal to 1/2 minus 1/2 cosine of 2x. Okay, so sine squared of pi x halves therefore is equal to 1/2 minus 1/2 cosine of 2 times pi x over 2. So these twos cancel out, and what I end up with is 1/2 minus 1/2 cosine of pi x. So now I'm going to substitute this expression into the integral. So I have n squared, the integral from 0 to 1, 1/2 minus 1/2 cosine of pi x dx, and I'm setting that equal to 1. So now let's use the properties of integrals to rewrite this as n squared, the integral from 0 to 1 of 1/2 dx, minus the integral from 0 to 1, 1/2 cosine of pi x dx, and this entire expression is set equal to 1. So we have two integrals. One of them is very easy to evaluate. The other one is going to require use substitution. So let's evaluate them. So the first one is the integral from 0 to 1 of 1/2 dx. The antiderivative of 1/2 is just x halves, and I evaluate that from 0 to 1. That is simply 1/2. Very simple. So the next one, 1/2 0 to 1 of cosine of pi x dx is going to require some u sub. So we're going to set u equal to pi x du, the derivative of u therefore is simply pi dx. So dx therefore is du over pi. So now let's make some substitutions. Let's substitute in dx, and let's substitute in u. And also we have to reevaluate our bounds. So u of 0 is equal to pi of 0, which is equal to 0. U of 1 is equal to pi times 1, which is equal to pi. What I'm basically doing is I'm substituting the original bounds into the expression of u. So that will give me my new bounds. So now I have 1/2 times the integral from 0 to pi cosine of u du over pi, which is equal to 1 over 2 pi times the integral of cosine of, from 0 to pi, cosine of u du. Basically what I did, I just took that pi out, and now we can evaluate. So I have 1 over 2 pi. The antiderivative of cosine of u is simply sine of u. So I have sine of u evaluated from 0 to pi. So that's 1 over 2 pi times sine of pi minus sine of 0. This sine of 0 is 0. Sine of pi is also 0. So this entire expression is 0. So that integral is simply equal to 0. And I'll continue the work on the next slide. Okay, so we just evaluated this integral. It's equal to 0. We evaluated this integral. It's equal to 1/2. So this expression becomes n squared times 1/2, which is equal to 1. Now I'm trying to solve for n because n is the normalization constant. So let's solve for n. I have n squared times 1/2 is equal to 1, so that means n squared is equal to 2. I multiply both sides by 2 to get rid of that 1/2. So n is equal to the square root of 2 plus or minus. So we usually just take the positive value just for convenience. So my normalization constant is the square root of 2. So now I can rewrite my wave function normalized. So psi was equal to sine of pi x over 2. And so now psi is equal to the square root of 2 times sine of pi x over 2. And that's my final answer. So in many physical chemistry classes, you won't be asked to explicitly evaluate an integral. Instead, you'll be given an equation that basically solves it for you. So I'm just going to set it up in case your teacher allows you to use that method. So we had the integral of sine squared pi x over 2 dx evaluated from 0 to 1 n squared. So our b in this case, so bx, we need to set that equal to pi x over 2. The x's cancel out, and I end up with b is equal to pi halves. So using this expression to evaluate the integral, I would get that my integral is equal to x halves minus 1 over 4 times pi halves b sine of 2 pi halves x evaluated from 0 to 1. And we can clean this up a little. So that's x halves. 4 times pi halves is 2 pi. And then the 2's cancel out in the sine expression, so I end up with sine of pi x. And that's all evaluated from 0 to 1. And then the process is exactly the same as the previous method, going from here.